Alright, so I'll go ahead and get started, I guess, for today. Sorry I couldn't be here, so sorry you're having to watch a video of this, but at the very least I think you guys need to pay attention to this one because it's the last piece of what you need to be able to complete the design for the fluorescent lamp ballast. Alright, so as you know, you should have seen an email about it. The lab is posted on the website. Okay, in the email I sent, it had a link to the site. Alright, once you're there, okay, you should be able to pull down a PDF of this thing. So all told, there's 7 exercises. Okay, a couple of them are building, and a couple of them are designing. Okay, all right. So in particular, it's once you get to this exercise 4 sort of prepares you for the design that you're going to do. Excuse me, in exercise 5, and then exercise 5 is where you're actually designing it. So you got basically a set of specifications, all right, and then you're going in here to actually do some of the design. All right, now something I haven't talked about much with respect to the website. There's a couple of things that you guys are going to want to know. One is in here we have this sort of useful data sheets section. So data sheets for parts that you're going to need. You click on there and you come over. So for instance, in exercise 2, I think it is, you're going to need 7404s. Okay, there's a data sheet for the 7404, easily accessible. We also have this available components thing. When you get in exercise 5 is when you're going to need this. Okay, for exercise 5, when you're doing the design, there's 2 cores you're going to be choosing from. Okay, one is this T400-52, and the other is this P36/22. All right, so when you go in there, it'll come in with data for that particular component. All right, so this is the data that you're going to need. Okay, and then similar for the ferrite core. All right, this also lists the capacitors and whatnot that are available to you. Okay, all right. Can't really ask if there's any questions about that, I guess. All right, so that said, we'll go through and we will take a look now at today's lecture, okay, in detail. One quick thing, that lab's due next Friday. I'm not going to be here until Friday this week, but I will be around pretty heavily next week in the lab with you guys. So I'll be announcing my own set of office hours when I'll be there. In addition to Ragood, we'll also be doing office hours. He and I will both be in there doing some stuff, so we'll definitely get some hands-on time together. Okay. All right, so this was the basic design that we've talked about here for the fluorescent lamp. Okay, you guys are pretty used to this by now. All right, so I've got the 2 MOSFETs which create a square wave for me, and then over here I've got my lamp connected across that capacitor. Okay. Now we've talked about the meaning of the C block. You guys should know that. That's basically to remove the DC component and to make sure that what comes in here is a pure AC square wave. Now before the lamp strikes, we've said a million times now, before that lamp strikes, effectively what we're dealing with is an open circuit. Okay? So if I were to draw the situation that we're dealing with here, okay, if I get rid of the effect of that C block, what I have is a square wave source. Alright, and then I've got this L and that C like that. Okay. This is before the lamp strikes. So the lamp is gone. Okay, here's C, there's L. And effectively I have here now a pure AC square wave. Okay. Now, effectively we said we can analyze this thing by saying I've got a sine wave right there. Now again, remember the reason for why we can use the sine wave is essentially because this guy is best represented with the Fourier series, which means it's got a fundamental term, and a third harmonic, and a fifth harmonic, so on and so forth. The only thing that's going to matter is going to be this. In exercise 4, you're going to validate that. The only thing that's going to matter is the fundamental term. Okay? Now, in this circuit, if you remember, the output voltage is going to become infinite if the frequency I drive it at is 1 over root LC. Now, up until now, what we've effectively said is, well, what we can do is we can think of this thing as having some sort of resistances that are going to limit that value. Okay, we looked at this in the last lecture for what would happen if we had an RL and an RC with that L and that C right there. Okay, so we've gone over that a little bit. The question is, what causes RL and RC? Well, for the inductor, winding resistance, and some other things that we'll talk about today. For RC, that's caused by some things about the dielectric. So in any real system you actually make, and you're making a real system in this particular case, all right, what we need to do is actually sit down and think about for ourselves what causes these things, what real components actually behave like. All right, a capacitor in general is not a capacitor. An inductor in general is not an inductor. Same thing for a resistor. Now, a resistor is not as bad. But we've got to talk about those real components, because when you get into real design, real components and how they behave are pretty important. All right. Okay. All right. So let's take a look at sort of today's notes. I basically said, okay, let's talk about the non-idealities of resistors, capacitors, and inductors. So you guys may want to tune out to some of this, but you probably shouldn't. All right, especially because the stuff on the inductors towards the end is really going to matter. So is the capacitor part going to matter quite a bit for your actual design. Okay, so I'll start with the resistors, but that's pretty basic stuff. All right, now some things you guys know. You probably are used to that picture of a resistor. Okay, you've dealt with that lots of times in the lab. And I would hope that most of you guys are actually able to read that resistor. All right, I'll talk about how to read a capacitor here as we go. All right, but that's something we'll get to. All right, if you don't know how to read a resistor, you should probably try to. If you go through that drawer in that lab upstairs, remember, you guys are going to find out that everybody's come along and just treated that thing like crap, and you're going to think you're getting a 1 kilo ohm resistor, and you're going to get a 1 ohm resistor, and it's going to blow up in your face. So just make sure you actually read that stuff. All right, here's 2 types of resistors. Now you can probably get a good sense of this one. It says 10W, 10 watts. Okay, so this thing's rated to carry some power. Now these are the ones that you guys typically use. All right, now this one is not rated to carry that kind of power. All right, so typically on a resistor, there's some key things we got to keep in mind, and they really do affect designs, especially if you need a precision design. All right, so if you're in the aerospace industry or the military, or you're designing something you really need some precision, you really have to be careful about what components you pick. You may think picking a resistor is simple, but it may not be. All right, so this resistor here, when it has, and you can't see that too well, when it has this gold band on it right there, it means it's got 5% tolerance. All right, so 5% tolerance, what's that mean? Well, if this is let's say, if I look at the colors on this one, I think this is a 68K resistor.